becomes soft, and at that time soft part and recording material, and the bulk becomes thin film, and the narrow particle, then multi-layer. In magnetism, we always call multi-layer. We don't say superlattice, and because different field always say that you use a different terminology. But anyway, magnetic multi-layer and the granule and the heterostructure and also salt membrane. Right now, actually, people use the salt membrane to do the magnetic material. These two journal actually is that actually when I was student, the first time I read the we call magnetism beyond 90s, and there was published a book actually by the Journal of Magnetism and Magnetic Material. And later on, in the 2000, they also published another book called Magnetism Beyond 2000. But 2010, they didn't do that because too many things happen. You cannot have only a book to cover everything. When I was a student, the first things I do is do some calculation, use the micromagnetic. I use the Cray XMP48. You need a liquid nitrogen on underground to healing the whole system. Otherwise, it will too hot, and the whole machine probably occupied like this room. Cray XMP. But however, this machine only can allow me to use the Landau-Lipschitz equation to calculate A by A and the local moment to interact with each other. And at that time, I use this one, and I get a history loop like this ugly shape. I still remember. And I talked to my experimental colleague. Nobody believed me. Because at that time, all the history loop is smooth. And my results saw a lot of steps. So nobody believed me at that time. And anyway, if you are initial all along here, and you will see one column reverse, then stabilize, then again and again. But later on, right now, if you do the micromagnetic calculation, it's so precisely. All the experimental data confirm actually it's the same thing. So actually at that time when I was graduate student, I'm quite frustrated, because I cannot compare with any experimental data at that time. But right now, after 20 years, everything predicted by this theory, and all the experimental data confirmed later. So seriously, if you are the student working on the theory, don't be so frustrated if you cannot see anything from the experimental data. Maybe after 20 years, everybody use those things to do the experiment. Okay, the spin dynamic at that time actually is that if you apply a field, initially everything in this direction. But when you reverse the field from the t equal to 0, then these things will be relapsed along the field direction. Finally, they will go to here. But at that time, we don't have late 80s, we don't have enough knowledge to study the spin dynamic from here to here, because actually the realization time is from gigahertz to terahertz, 10 to the minus 9 seconds to 10 to the minus 12 seconds. So it's quite fast. No matter experiment of the theory, it's not easy to analyze these things. And if you see the spin dynamic, actually the time scale is like this. And the storage time, usually you ask for the 10 year for storage. And so the reasonable storage time, magnetic recording is about 10 to the 10th second. And this is second. However, what you want to study actually is the giant magnetic precision time. It's about this range. But if you at that time you only have the unique, so the field studied here we call the spin dynamic. But at the early stage you only have the NFN of smoke, and that is too slow to study the spin dynamic. Right now use the laser pump and the ball method, you can do something on that. So actually we also try to make the narrow scale magnet at that time. And the top-down method actually is narrow imprinting. It's by Stephen Cho right now in Princeton University. And when he did this, he was in the University of Minnesota. and he used the narrow imprinting, something like the way, you know, the ancient China time, they make the 活字版 to make the character actually on the book. But anyway, the bottom up actually is a self-organized magnetic array, we call SOMA actually. And but this one actually is all those two ways can be demo small scale but not large scale. But anyway, at that time also a lot of way to new method to be invented to measure narrow scale magnetic response. So the very powerful way, actually semi-classical way to analyze the narrow magnetism and micromagnetism is that we include in the exchange energy, anisotropy energy, and the external field, and also the magnetostatic energy, also including the thermal things, Langevin dynamic, and to analysis this one. And the main idea is phenomenological equation is the dynamic, you know, of the time dependent of the magnetization should be depend on the first term. Actually, is Larmor precision. It's some kind of any cross edge. They have the top. However, if this is a damping term, you need to have damping term. Otherwise, your magnetization cannot relax to the field direction. This is the angular preserved rotation, but you need one damping term. And this is the only way you can get the Landau-Lipschitz equation. This is a phenomenological equation. But the mathematical you can prove this is the only possible form. And the way actually is that the magnetization use the first Larmor precision, use the angle preserved actual rotation. Then you need another is a damping term, push them into the field direction. And very easy, you know, idea and equation, but however turns out to be very powerful right now because of computer, you know, facility. Such as this one is that we use actually some thin film material, use the Landau-Lipschitz equation, thin film material with elliptic actually shape, and the shape is like this. Because the exchange force, the sample size is too large, exchange force cannot dominate. So if you initially you saturate in this direction, all the arrow along the left direction, you reverse the field, and you turn it on to here. And it turns out to be, you will see, actually it turns on, because the exchange force cannot dominate. You cannot lock all the spin together. So they will become vertex, and such as some vertex comes out, and the vertex and gradually, you know, move along the transfer direction of the field direction, and finally push out, and finally everything, you know, goes like this way. So if you have large sample, they will always behave like this. But if you have reduced the size only by half, you know, such as 190 nanometer long in the long axis and the 16 nanometer in the short axis, 30 nanometer in the z direction, and then you do the same thing. Then exchange force actually is dominant. Then they will reverse, lock together like the macro spin, all together. They will gradually, you know, all lock together, and the shape effect is not so important, because actually exchange force dominate. Then they want to reduce the energy or exchange energy, so they lock together and reverse like this. So the size actually is quite important for everything. Okay, that's for the magnetism side. Before on the late 80s, and another field actually is electronics. If you go back to the electronic, actually at first the calculator is a mechanical electronic. They use the mechanic to do the add and the minus and the addition and the minus. And later on, actually, the first generation actually electronic calculator came out. It used a vacuum tube, and then the second generation used is 1948. Then the IC comes out, the VLSI comes out, Intel, and they move very fast. But anyway, the first electronic calculator actually was done by 1946, and actually the speed is only 5,000 floors per second, and they took about, the whole area took about 1,000 square feet, and that's a very huge machine and a very slow machine. And on the late 1946, they changed very fast. So right now, actually, you know, the semiconductor industry actually, they have the very proud Moore's law, and it goes, you know, very smoothly and predictable. And one of the main reasons, as I mentioned, from the history of the magnetic, we know this is because of the technology actually based on the same physics law. If you introduce a new physics law, the slope should change. But anyway, because they miniature actually the things every 2 years. So finally they will meet two problems: atomic limit for the unit, also quantum fluctuation. But this actually is not the most tricky things. The most tricky things is the power assumption and also heat transfer. When you become very small, the heat accumulation actually become very significant because Joule heat. Actually, they use a lot of the heat accumulate. You need to, you know, cool down the system. It's not as easy. Actually, Joule heating is a real bottleneck when you scale it down. So the net result is that even though you can scale down, your performance probably will be dropped because of heating problem. So your performance probably will drop. So even though Moore's law can keep going on, probably the optimized performance will be in somewhere. If you don't have the new concept of the physics to change your technology. So what we should do next? It's lucky actually we identified the Spintronics, you know, on the late 80s, early 90s. Actually, carbon actually gives biology, but silicon gives the geology and the semiconductor technology. This is from Kittel. But if these things cannot be keep on going, what will be the future? If we go back to the history of human life, Stone Age, Bronze Age, and Iron Age. So the high tech is similar. Silicon is some kind of stone, and they use the copper wire right now. So the only things they forgot is the ion spin. They need to use the spin. So actually it's similar. I think the high tech sooner or later will move to the ion age, which means the spin age. Actually use the silicon and the charge. Silicon use the charge and plus the copper wire. But right now they are approaching limit. So to try other materials spin is quite a you know intuitive idea. But this idea, even though it's simple, but it's non-trivial. Actually, you need to thank for these three gentlemen: Stuart Hawking, Eberford, Peter Gruber, Germany physicist, and French physicist. They got Nobel Prize actually on 2007. Stuart Hawking actually made the things become practical. Okay, yeah, 1988. I think the main reason is that, you know, we used to learn the electron only can use the charge because we don't have the microscopic way to do that. If you use the microscope on the narrow scale, I will mention why is that. You will identify the electron really have the up spin and the down spin. Just like if you take a close to see, you see far away, you only can identify they have the property of the charge. But if you have the close enough, you will see they will up spin like down spin, just like human. Always you see close enough, you have the man and the man. So actually, let's provide a new degree of freedom for the solid state. Even though we know spin for quite a long time, but we never think we really can manipulate that in the real life. So they provide a new degree of freedom for the solid state. It's just like, you know, these three gentlemen, just like the prince kissed the sleeping beauty and the woke heart. And right now, everybody knows he is so beautiful. The spin actually is, for electron is an old story in physics. But the physicists never try to, you know, push out to the real life. But back to the 1891, the Irish physicist Stoney already proposed they have a unit in electricity, and he named the unit as electron. At that time, it's just a concept. So actually later on in 1897, Thomson identified that they do have the electron and carry on the charge. In 1922, Stern-Galax experiment identified they also have another property called spin. And the theory actually was proposed actually, Pauli actually first introduced a two-value content degree to construct the Pauli equilibrium principle to explain the different electron can only have different quantum state. He proposed this, idea in the very beginning. This actually is Pauli. And 1925, actually, Uhlenbeck and Goodsmith actually identified this quantum spin as a spin. Actually, they have side stories. Chronic actually was a postdoc actually on for the Pauli. Actually, at that time, he suggests this is the same idea to Pauli. But Pauli's response at that time is that he said this idea is an idea from an idiot. But later on, so that's the reason why the Chronic doesn't get a Nobel Prize, and the Uhlenbeck and Goodsmith get a Nobel Prize. So when you say something creative to your supervisor, if he say you are an idiot, don't trust him. And 1927, Pauli used the Pauli matrix actually to represent spin operator on these two-component spinor wave function. And Dirac actually pushed that into the relativity form, Dirac spinor. Actually, they complete the concept of the spin. Actually, even nowadays, we still use the similar idea and the similar formula to explain the things. They say Heisenberg, very young and how do you say that? Handsome person. This is Dirac, and Professor C.A. Young quite like him. He used one word to describe his article. He said, "Oh, his article just as pure as like the water in the springtime." So if you check nowadays on the Oxford Electron Dictionary, what is spintronics? Spintronics is a branch of physics concerned with the storage and the transfer of information by means of electron spin in addition to electron charge as a conventional electronic. So actually, right now, even in the English dictionary, on Oxford, they already have explanation. But the first generation actually is on early 90, actually is independent explorer up and down. But right now, actually, second generation, we want to use a quantum combination of the things. So actually, jamming, resistance, colossal resistance is somehow the collective behavior of the spin. And right now, we want to use the individual, the combination of quantum state. This one actually is the Spintronics since 1980, all the development. Actually, I was student around this area. On the 1987, actually, high temperature superconductor was identified. At that time, it's heat to all the physics, much stronger than the wave right now for the Topological insulator. Almost everybody switched to that field. And 1986, actually the whole story comes from 1986. This is the multi-layer system. Actually, here is the magnetic thin field. In between them is non-magnetic. And for the last 40 years, if you take a look, they just changed the spacer from conductor, insulator, semiconductor to superconductor. Every 10 years, they change one material and make the spintronic behave in a different way. I was a graduate student, I think, around this area. So I stay actually in the magnetic things. On the early 80s, in the magnetic field, we have quite a puzzle things at that time. Because usually magnetic at that time, because the technology is not so good, so we only can study the bulk material. So because semiconductor industrial improved, so people can start to study the thin film material. So I still remember around 1985 or 86, one experimentalist in UC San Diego, and right now it's quite famous for the left-handed material. Shelley Schultz. He first person to invent the rectangular material in experiment. He came to me, asked me one question. He said, right now we can make one single layer of the ion. And however, we still found the spontaneous magnetization. He said, can you explain that? Because if you know the history, because you know, at that time we have the Merman theory. If you reduce the three-dimensional magnetic, you have the, in three dimensions, you have spontaneous magnetization. If you reduce the two dimension, then because of quantum fluctuation, you will not observe the spontaneous magnetization. And he said, hey, come on, our experiment already did that. Your theories are wrong. and he come to me and asked me to know why. And later on, actually, we know why is that, because it grows on the substrate. And they induce some, you know, anisotropic. And also some kind of the thin film is not as pure as a single unit. They have compound, actually, complex structure inside. They have internal degree of freedom. But what I want to say, on the 85, people start to know how to make the thin film in the magnetic. And later on, they make the multi-layer, just like magnetic, non-magnetic, magnetic. So in 1986, one group in AT&T, and also Peter Grunberg group, published one paper, separated. And Peter Grunberg group, and also Rainier Gore's group in AT&T, they identified actually the magnetic, two magnetic layers will observe the anti-femoral coupling when you change the spacer thickness. And they some kind of the RKKY oscillation. They already identified on the 1986. However, 1987, suddenly superconductor, high temperature, high temperature superconductor was identified. Everybody switch. They have 2% doesn't switch. One is Eberford, the other is Peter Grunberg. And the Rainier Gore group in AT&T, the whole group switched to the high temperature superconductor. And that is one possible reason this Nobel Prize doesn't go to AT&T. But so when such as topological insulator heat came right now, I still advise you, some of you need to think it over very carefully. Don't jump too fast. Maybe your original work can get Nobel Prize. But anyway, 1987, most people go to, but Eberford and Peter Grunberg still stay in that field. It's not easy for them to get the funding at that time, but they still. 1988, they published two papers separately. One, Eberford published a paper in Physics Review Letter, and Peter Grunberg published a little bit later in Physics Review. However, he filed a patent first for this material. So right now, the Peter Grunberg Institute make a lot of money every year. A further group doesn't make money. But anyway, this is a discovery of the giant magnetic resistance. So if you want to have a good, discovery, sometimes you need to be persistent, stay steady. Don't, move by other person. But anyway, it's not easy actually at that time if you don't move away. I didn't move out because I have a talk with, the Professor Harry Schuller at that time, quite a famous solid state physicist. And is a professor actually in the UCSD physics department. I have a chat actually at that time. I asked him, at that time he doesn't move to the superconductor also, even though he do a lot of calculation on similar thing. I asked him why you don't jump into the superconductor, and he told me one very interesting thing. He said the experiment identified the superconductor on the 1905, but people realized after 50 years, and on the 1957 they proposed the theory, and he expected at that time he told me 1987 he told me he expected this strange phenomena only can be identified after 100 years. and he is too old to do those kind of things. but anyway, But for the dry magnetic resistance, when it identified, the main reason he pushed so fast, the fundamental research, they had invented the spin valve. This is also from Germany, the spin valve idea pattern. But Dini, I think it's from Dini group. And then, you know, some kind of specular scattering, and also, you know, narrow oxide layer and the hot metal, all those fundamental things. But the most important things, if you want to have the persistent and good funding support, is application in the cancel out. Actually, the application cancel out very fast on 1994, joining the resistance and came out. I still remember they have a 3N conference in 1992, actually in Minnesota. At that time, I attended that conference. Everybody was so excited because people know the application will soon come out. So they changed the whole magnetic recording industry after that. And because they are so successful, so quite a lot of money and the research funding pumped in. So then they changed the conductor into the space insulator. Then turn out tunnel magnetic resistance comes out. Then propose N-ring comes out. Also, all the industrial application comes out. And the semiconductor actually also dynamic semiconductor spin transistor. Then the spin Hall effect and the spin logic device was proposed. And superconductor. But I think the semi-classical way, the model of the Drew model, if you consider why, you know, those things will only happen, you know, observed in the after 1988, they have several reasons. One is that actually because if you use the Drew model, explain this. Because electron have the charge and the spin, and you can consider semi-classical way, and the up spin with this and down spin with this, counterclockwise and clockwise. And if you have two electrons, and they all carry the charge, but they have different spin. So when they transport into the media and the material, and they were scattering by the different way. Some kind of the scattering will be within the mean free path range. They have some kind of possibility for scattering. And if they have the, you know, spin dependent scattering, the charge will not disappear during the scattering, but the spin will always, you know, flip over during the whole transport area. So if your transport region is much larger than the mean free path, then your spin in the average, they flip more than 1 million times. So actually the spin property will be forgot, but the charge is still maintained. So usually if you cannot go to the narrow size, you always cannot use your spin collective in the transport phenomena, but you can use actually the charge. So actually the spin, even though they carry on, but in the average they forgot actually. And that's the history for the Spintronics. If you take a look at history for the insulator, actually the insulator comes from energy gap. So they have a lot of reasons of the energy gap. The band insulator actually is a periodical lattice provide some kind of the gap. And also Morse insulator, due to the electron interaction, many body actual physics lead to the gap of the charge excitation spectrum. And they have a lot of different kind of Morse insulator was identified later on. And also Pierre actually insulator, actually electron with the, you know, the deformation actually comes from that. And also Anderson insulator comes from the disorder or impurity. And in the late 1980s, they also have the quantum Hall insulator because actually it comes from the quantum Hall effect. And right now people identify actually for spin electron, you also get the 2D, you know, two-dimensional topological insulator or quantum spin Hall effect. Actually we call the topological insulator. Actually this name was named by the Professor Moore from the UC Berkeley. And the topological insulator actually was contributed by all those people. Actually, they have the different, you know, spin up and the spin down electron transport on the edges. I'll explain more detail later on. But the reason why we call the topological insulator because actually conventional insulator and the topological insulator really behave like a different way. Actually, topological insulator, for myself, is not a good name. But Professor Moore always mention it's a very